So today what we're going to do is we're going to recall how we did division. So first of all, if we ever think of division, if you had 17 over 8, we would look at it as an improper fraction, right? And then you also had 8 over 16, which was a proper fraction. Now, those fractions, we would always kind of use those to represent division. So let's talk about this. Let's say I have the following. If I had the following, I said 882 over 25, right? This top half we would call the dividend. This is called the divisor. Okay, so that's what we would start off. So the thing that we're dividing is what's on top of the fraction. And when we are doing our calculations, so let's say we went and said 1882 and we were dividing by 25. So remember, we said that this is the divisor. And then this is the dividend. Okay. Now, because we have the divisor and dividend, there are two other things that we need to see. So let's say we have 1882 and we're dividing by 25. Well, we know that 7 goes into 1885, doesn't it? Sorry, 17 goes in 7 times 25 goes into 188, so you get 175. And then we subtract that from there. So we end up with 13. Then we carry down a 2. So now we have 132. So now 132 can be hit with 5 times 25, which gives us 125, which gives us 7 at the end. Notice I'm going to put my 7 in a box here. Now, this we call the remainder. And this thing up here, we call the quotient. So here is how all of this stuff kind of works. So for any function, so for anything, we have, so let's say I have f over g, right? And these are both functions, right? You would get the quotient of x, the quotient number, plus the remainder of x divided by d of x. That's what we're going to be working on today. Now, here is an analogous form from what we just learned right here. So let's say I have 1882 and we divide by 25, right? So when you take 1882 and divide by 25, the answer is given as this, 75. I'm going to put that in red, which is our quotient, plus the remainder, which is 7, and then divided by 25. So analogously, that's what we are calculating today. Okay? So I'm going to talk to you about how we come up with solutions for our mathematics. Okay? Now, let's go and do the formalities. So here's what you need to know. So if this is true, I have f of x and d of x, where d of x is not 0, right? Where fx's degree is greater than or equal to the degree of fx, then we have two polynomials. And those two polynomials that we have extra are qx and rx, right? such that this is true. If I take fx over d of x, remember, d of x is like our divisor. Okay. Then we get the following. Fx is equal to the following. Qx, which is like our quotient function, plus Rx divided by d of x. Now, this also means that fx can be calculated by using the following. Dx times qx plus r of x. So, if I ever wanted to say that something is equivalent to something else after I've done my division, then I say the divisor times the quotient plus the remainder is equal to the original. Okay? So just take a moment and just copy that down. So we have a theorem that we need to understand. Okay? So here's what you need to know. Let's say that I have something like this. A function defined as f of x is equal to x minus c times, well, remember that quotient thing? Q of x plus some bit r, right? So now here's what would happen. If I had f of c and I punched that into my equation, I'd have c minus c, which is 0, times q of c plus r. So here's what you would know. You'd get f of c is equal to, well, just r, right? And that would only happen if r was not equal to 0. So if r was not equal to 0, then we wouldn't have a 0, right? So this is what the remainder theorem says. So if a polynomial fx is divided by a linear polynomial, say x minus c, then the remainder is just f at c. So let's go and use that with long division. So imagine I say, okay, find rx and qx. So find the quotient function and the remainder function, given that I have fx is equal to the following. We've got x to the 6th times minus x to the 5 plus 10x cubed plus 1, and we're going to divide it by the divisor function, x squared plus x plus 1. Now, here's how you set this up. When you do this problem, you literally have to just basically start with your divisor, which is x squared plus x plus 1. And then we're going to divide it by everything in here. So we're going to start with x to the 6th, our highest power. Then we're going to put minus x to the 5. Now, because there is no x to the 4 here, what we're going to do is we're going to put plus 0 x to the 4, and then we continue down 10x cubed plus 10x cubed. And now remember, we also have no x squared term. So what we have to do is we're going to have to put plus 10x squared. Not plus 10x squared, plus 0x squared. And then we end up with 0x squared plus 1. So now here's how we solve this problem. So what we do is we start by looking at the x to the fourth leading coefficient here, and we're trying to match it with some leading coefficient on this thing here. So because we've got that, what we're going to do is we're going to say, okay, we've got x to the 6. So what we're going to do is we're literally going to do this. Just going to zoom in here. All right, so we need a 1 x to the 6. So here's what I do. I say, okay, so because there are 3 numbers here, the number that we're going to multiply this whole thing by is not a number, but x to the 4. So we're going to use x to the 4, and we're going to multiply it by everything here. So x squared becomes x to the 6. And then we have x to the 4 again. X to the 4 again. Multiplying by the following x. So you're going to have plus x to the 5, and then plus x to the 4. Now, the key idea here is to remember that when we were doing our division, every time we got our 3 terms, what we would do is we would subtract those 3 terms from the original. So x to the 6 minus x to the 6 is gone. But negative x to the 5 minus x to the 5 gives us minus 2 x to the 5. Okay? And then we have 0 minus 1, which gives us negative x to the 4. So now, just like before, we would always carry down. So when we carry down, when we bring down, we end up with 10x cubed. Now we have another 3 terms here that we're literally going to try and eliminate. So we need to multiply the leading coefficient by negative 2x cubed. So let's do that. So we have minus 2x cubed. So multiply through, you're going to get negative 2x to the 5, and then minus 2x to the 4, and then minus 2x cubed. And now we take our moment and subtract. So the only thing that should cancel should be the front end of this. So we're going to subtract. So I'm going to put a circle with a minus in it to remind myself I'm always subtracting. So negative 2 minus negative 2 gives us 0. Negative 1 x squared, x to the 4, minus 2x to the 4 really means plus. So minus plus 2 gives us, minus 1 plus 2 gives us x to the 4. And then the same happens for this, so we end up with positive 12x cubed. Now we must bring down the next value. So we have 0x squared. Okay, now I made a mistake in our problem, so go back up here and make sure that you put, instead of plus 0x cubed, we have to put 0x squared, 0x plus 1 at the end of this problem here. So remember, it's x to the 6 minus x to the 5 plus 0x to the 4 plus 10x cubed plus 0x squared plus 0x plus 1. Because when we did this problem, you'll notice that in our original function, we were missing an x squared and an x term in our polynomial. So remember, any of the placeholders that are missing, you need to make sure that you put them in. That was the main reason I left that out, so that we would remind ourselves to go and put that in. So now, for this next bit here, we still have, we're going to get rid of the x to the 4 term. So we need to go and take our problem, and we're going to basically multiply by x squared. by x squared. So we end up with x to the 4 plus x cubed plus x squared. So now we subtract again. And the zero coefficient, the zero number in front goes away. So x minus x goes away. And we have 12. 12 minus 1, which is 11x cubed plus 0 minus 1, which gives us, instead of plus 1, it becomes minus 1x squared. So now we're going to bring down the 0 x term, and we pull it off again by noticing that there's an 11x cubed. So we're going to have to go and kill this off by using an 11x to kill off that. So now we're left with 11x cubed plus 11x squared plus 11x. We subtract once more, and we're left with, at the bottom, this is gone. And then you have negative x minus 11, which gives us negative 12x squared. And then 0 minus 11 gives us minus 11x. And then we bring down the 1, and we're almost done. So now we bring down the 1, we're almost done. So now we have plus 1. So now let us zoom out and focus on what we have to do for the last bit of this problem. So remember, we went through all those steps, and every time we were doing this, we always killed off the first coefficient of our 3 numbered term, which was always multiplied by these things. So now we have minus 12x squared. So the last thing we're going to subtract is minus 12, right? And because we're taking minus 12 off, we get minus 12 x squared minus 12x minus 12. We subtract this. Now, you're going to see me put a box around something when we get to here. This is always my remainder. This makes my calculations easy. So we got 12 minus 12. Boom. This is gone. And then we have 11, negative 11 minus negative 12, which is really plus 12. So a negative 11 plus 12 is x. And then 1 plus 12 gives us 13. So this is our remainder. And how do you know you have a remainder? The power is less than the dividend. Okay? The power is less than the dividend. And so that's your remainder. Now, remember, if I ever asked you, I could tell you, I could say, use long division to find QX and RX, given all that stuff that we had here. Okay? Very important, right? Very important. So now what we're going to do is I'm going to basically take all this information, and what we're going to do is we're going to write fx in terms of our qx, our quotient, our divisor, and our remainder. So you can say fx is given by our original equation. So this is true. Here we go. This is going to be a long one. All right, so fx, we'll write this in blue. Fx is just, well, x to the 6 minus x to the 5 plus 10x cubed plus 1 is equal to our quotient, our divisor, which is x squared plus x plus 1, and then times our quotient, which is x to the 4 minus 2x cubed plus x squared plus 11x minus 12, and then plus our remainder, x plus 13. So in black. So this was the original. So that's the original. This is the divisor. This is the quotient. And this is the remainder. So anytime you're doing these problems, this is what I want you to write as your final solution, where you show me the entire equation. Okay? So take a moment and immerse yourself in the glory that is division, that is polynomial division. So use the remainder theorem to find r, given that fx is equal to 2x to the 4 minus 7x squared plus x minus 1, and we're going to divide it by d of x is equal to x minus 2. So here's what the remainder theorem says. Basically what you're doing is you set x minus 2 equals 0. You solve for x, x is 2. So now you're going to take that and plug it in to f. So you're going to get f of 2 is equal to 2 times 2 to the 4 minus 7 times 2 minus 1, which is, well, 16 times 2, 32 minus, 2 squared. That's 2 squared, 7 times 2 squared, which is 28, minus 1, which is 3. So f of 2 is 3. Therefore, the remainder is 3. So you could say, if the remainder is 3, then clearly, d of x does not divide f, otherwise known as, are you ready for it? D of x is not a factor of f. That's all you need to know. Okay, for the final example, I want you to copy it down. It's on the website. And it shows you how to find a k value if I give you a k value in an expansion. Okay, copy it down, and then you're going to do the following questions. Page 143, numbers 1 to 21, and those are the odd numbers. And then you're going to do number 39. Okay, that's it.